Okay, doing guided practice for test 2 review. Sorry about Gunter. Alright, so we're looking at a spring oscillator set up in the diagram. It's at an angle, but it's giving us our K value, so you don't even need to worry about like the component forces on that thing. We already know what K is. Okay, so for 1A, I, and it's 5,000 pieces. Looking for the period of oscillation, we've got the period of a spring, which is going to be 2 pi times the square root of mass over our K value. Okay, so in this case, we've got a K value of 12.25 newtons per meter. Okay, that's our K value. We've got a mass of 0.5, so 0.5 divided by that, taking the square root of that and multiplying by 2 pi. Okay, so that gives us a period of oscillation of 1.27 seconds. Okay, now B, the frequency of oscillation. Frequency, that's not B, it's II. There we go. Frequency of oscillation is just the inverse of your period. So 1 over that period we just found. So just taking that to the -1 power. Here we go. We end up with a frequency of 0.788, frequency measured in hertz. You can also do seconds to the -1. That's perfectly fine as well. Angular speed. All right, 2 ways we can find that. Omega is just the angle it's covering. So in this case, 2 pi, since we're looking at one full oscillation, divided by your period, or you could also do 2 pi times your frequency. Doesn't really matter which one we go with, it'll give us the same answer regardless. Okay, so 2 pi times our frequency. Let's do that. So that gives us a angular velocity of 4.95. All right, if you're using this formula here with that 2 pi, that means that our angle is in radians, because that's one full rotation. Okay, so there's going to be radians per second. Okay, 4, max speed of the car. Okay, so the max speed, whenever you're looking at something in simple harmonic motion, is just going to be 2 pi times our amplitude, basically one full circumference, divided by our period of oscillation. Okay, so 2 pi a over t gives us 2 pi. It says that we're stretching it out 40 centimeters, so that's our amplitude there. So 0.4 is going to be a, divided by our t, which is 1.27, okay, which gives us a maximum speed of 1.98. All right, our distance here was measured in meters when we plugged it in, so this is going to be meters per second. Okay, for V, for our max acceleration of the cart, all right, so max acceleration is going to be 4 pi squared a over t squared. Okay, alternatively, you could also use omega squared x. And since your maximum acceleration is happening at the point that's furthest from the equilibrium point, your x there would just be your amplitude. Basically, this omega here is what you end up, like omega squared, that's where this 4 pi squared over t squared came from, right? Because omega is just 2 pi over t, so squaring that, you end up with 4 pi squared over t squared. All right, so either of these will give you the same answer. So in this case, let's do it the long way. So we got 4 pi squared times our amplitude of 0.4. divided by our period squared, so 1.27 squared. Okay, and that gives us a maximum acceleration of 9.79 meters per second squared. That's really close to 9.8, which means that this ramp is significantly steeper than it looks. Okay, and next, maximum restoring force on the cart. Okay, so maximum restoring force, we can just use F equals NA here. Okay, where our mass is the 0.5 and our acceleration is what we just found, the 9.79. Okay, so 0.5 times our last answer, that gives us a force of 4.895. I should just round that up to 4.90, whatever. 4.895 newtons. There we go. Next one, looking for the speed of the cart when it is 25 centimeters from the equilibrium position. Okay, so one of the ways that we can look at intermediate speed is that our intermediate speed is just equal to our max speed times the cosine of our angle. One way that we can find our angle is the inverse sine of x over a. Okay, So we've got an x here of 25 centimeters, so that's 0.25, divided by our amplitude, 0.4. Okay, taking the inverse sine of that. Okay, and then taking the cosine of that. All right, so that gives us 0.78, multiplying that by our maximum speed, which is 1.98. That gives us our intermediate speed of 1.55 meters per second. Okay, looking for our maximum kinetic energy of the cart. All right, so kinetic energy is just 1/2 mv squared. Okay, and our V max was the 1.98, so that's just going to be 0.5 times 0.5 for our mass, and then 1.98 squared. So that means our maximum kinetic energy is just going to be 0.98 joules of energy. There we go. So there's number one. Wait, no. No, it isn't. That's just A. Oh, this is a long one. All right, let's look at B now. So B, state the position at which the maximum values of these quantities occur. So speed. If you're looking at this thing oscillating back and forth, it has to change direction at the bottom and top of its motion, which means that its fastest point is going to be right in the center, right at the equilibrium point. Okay? Its largest accelerations will be wherever the spring is most compressed or most extended. Okay? So that'll be at the ends of its motion. If this thing was labeled A, B, and C, you would have your largest accelerations at A and C. Okay? Restoring force will be the largest whenever your acceleration is the largest, because we got F equals ma. Okay? So your restoring force will be largest at A and C as well. Okay? And kinetic energy. So kinetic energy is proportional to the square of our speed. So the larger the speed is, the larger your kinetic energy will be. Okay, so at A and C, it's changing direction. You've got no speed there. All right, which means that B, that's going to be your largest kinetic energy because that's where your speed is largest. Okay, potential energy. There's more potential stored inside the spring, the more it's compressed or stretched, which means that you'll have the largest potential energy at A and C, just like where you had your largest acceleration and force. Okay. For C, sketch the curves representing the change in each of these quantities over time. Show time on the x-axis. Okay. So for our first one, we're looking at displacement. Okay. We're going to go through one full period here. All right. So this thing is starting at 0 degrees. Okay, so 0 degrees means right at equilibrium. All right, at equilibrium, its position is at the equilibrium point. All right, then as it swings, as it goes through a positive angle, all right, as you're going up to 90 degrees, your displacement will get larger, up to a max at 90 degrees. This will be whatever your amplitude is, whatever that height on that line is. Okay, then it's going to go back to the equilibrium point. All right, so swinging there, swinging back. Okay, after that goes the same amplitude on the opposite side. So now negative, and then back to the equilibrium point. Basically, your displacement graph is just a sine wave. Okay, so starting at 0 and then going through a wave there. Okay, and velocity. Okay, thinking about it over the same scale. It's the slope of this graph, so that's one way we can think about it. Like it's starting off with a positive slope, 0 slope, negative slope, 0 slope, positive slope. The other way we can think about it is just thinking about how this thing's moving. All right, so at the equilibrium point, that's where it's going to be moving the fastest. All right, so we're starting with it at its maximum value. Okay, 90 degrees later, now it's at one of the ends of its motion. At that end, it's going from a positive velocity to a negative velocity, which means you're right at 0. Okay, so this is when we're at the equilibrium point at our speed, not at the equilibrium point, at one of the ends for our speed. Okay, then it comes back to the equilibrium point, but now it's going the opposite direction, so you end up with a negative maximum value, and then back out to an end where it slows down to a stop, and then back to its original location. Okay, so instead of a sine wave, we have a cosine wave. Okay, and looking at the slopes of this displacement graph, you can see that happening. You've got a positive slope, positive value. No slope, 0. Negative slope, negative value. No slope, 0. Positive slope, positive value. Okay, the velocity graph is just the slope of this displacement graph. Okay, now our acceleration is the slope of this graph. Okay, so at the beginning of this, our slope, it's starting off flat, which means our acceleration is starting at 0. Okay, here our slope is at its steepest and pointed downward. We've got a maximum negative value. Okay, here our slope flattens out again, slope of 0, which means no acceleration. Here, positive slope. Okay, and that's the most positive we'll be getting, so we've got a maximum positive value. And here it flattens out again, so going back down to 0. Okay, so you're comparing the displacement graph and the acceleration graph. They're inverses of each other. All right, so this one, positive sine wave, this one, a negative sine wave. Okay, so if you're looking at these graphs, displacement will be a sine wave, velocity will be a cosine wave, acceleration will be a negative sine wave. Okay, and restoring force is equal to mass times acceleration. Your mass isn't changing, which means that this thing is just going to be another negative sine wave. When your acceleration goes up, your force goes up. When your acceleration goes down, your force goes down. Direct proportion. Okay, and then the last one, total energy. Okay, so thinking about this thing is it goes back and forth. Right? You've got it constantly changing between kinetic energy and potential energy. But at any point, you'll have the same amount of total energy because that energy is coming from those two types of energy. It switches between the two. As it speeds up, it goes to kinetic energy and you lose potential energy. As it slows down and stretches the spring, you're losing kinetic energy, but you're gaining potential. Right? So whatever total energy you have is maintained the entire time. Okay, so energy, your total mechanical energy, will be the same throughout. Okay, now on to number 2. Okay, so number 2, a pendulum swings back and forth as shown in the diagram. The equilibrium position is labeled point A and the endpoints are labeled B and C. This period of the swing is 1.42 seconds. The amplitude of the swing is 10 centimeters. At what point is the pendulum bob moving the fastest? Okay, so 1A. Be moving the fastest when it's not changing direction, so right at A. All right, at B and C, it has to change from going a positive direction to a negative direction. So the number between positive and negative, 0. Okay, so moving the fastest at A, at equilibrium. 2, experiencing the greatest acceleration. Okay, so right at A, that's where it's at equilibrium. It's relaxed there. It's not being pulled up or down, which means it isn't going to be accelerating up or down. Okay, so you're going to have your largest acceleration at the points that are furthest from that. So largest acceleration at B and C. Force, your restoring force is directly proportional to that acceleration, so the larger the acceleration is, the larger your force is going to be. Okay, so your restoring force will be largest at B and C, just like your acceleration was. It will be not moving when it's changing direction. All right, so going from left to right, it's changing direction at B. Going from right to left, it's changing direction at C. All right, so right in between, positive and negative, that's where your 0 is. So not moving will be at the ends of its motion, B and C. Experiencing no acceleration will be where it's relaxed, so that'll be at point A. Experiencing no restoring force, well, where you've got no acceleration, that's where you've got no restoring force. So that'll be at point A. Okay, so there's all of A. Hooray. Look at B. Frequency of the swing. Okay, that means we're going to have to go back and get some values. All right, frequency of the swing. We've got a period. All right, and frequency is just the inverse of period, so 1 over t. Okay, so we've got 1.42, taking the inverse of that, that gives us a frequency of 0.704 hertz. Got a frequency now. Fantastic. Up next, the angular speed. Okay, so angular speed is just 2 pi times our f. All right, we've already got our frequency, so we're just going to do 0.704 times 2 pi. Okay, so angular speed of 4.42 radians per second. There we go. 3, speed of the pendulum bob at point A. Okay, so at point A, that's where it's moving the fastest. Okay, so that means we can use our max speed equation. We can use this Vmax equals 2 pi over t. Okay, so 2 pi over, 2 pi a over t. Lost my mind. 2 pi a, 10 centimeters. So 2 pi times 0.1 divided by our time of 1.42. There we go. So we end up with a maximum speed of 0.442 meters per second. Cool. Up next, for C, we're looking for the following when the pendulum bob is 5 centimeters from point A. Okay, so when we're looking for that velocity there, that means we're looking for that intermediate velocity, which is just our max velocity, max, there we go, times the cosine of the inverse sine of x over a. Okay, so our x, we're looking at 5 centimeters, so 0.05, divided by our amplitude, which was 0.1. Okay, so now inverse, sorry, yeah, forgot an inverse on here. Inverse sine. Okay, so inverse sine of that, cosine of that. Oh no. Oh no. I just realized my calculator is on degrees. Crap. That means this is going to be wrong. Okay, so this value is going to need to change. Yeah. Hold up. Okay. Let's real quick go back to this one. Okay, so x over a for 1a vi. Okay, so we've got a maximum speed of 1.98. Oh my god. 1.98 times the cosine of the inverse sine of our displacement over our amplitude. So our displacement on this one was 25 centimeters. So 0.25 divided by our amplitude of 0.4. Okay, still ends up checking out. All right, we're good. Never mind. Carry on. All right, so back to this thing here. CI. No, this, God, throwing stuff all over the place. Of course, it's another review, which means I need to lose my mind again. That's what happens when I accidentally kill a fish. Sorry. So this one, we're 5 centimeters. Okay, so we got 0.05 divided by, what? 0.05 divided by 0.1. Okay. And we're taking the inverse sine of that answer, and then the cosine of that. Oh, that's why it ended up still being fine. Okay. Times our max speed of 0.442. Okay, so that ends up giving us a intermediate speed of 0.383 meters per second for the pendulum. There we go. All right. So now the acceleration there. Okay, acceleration, when you're looking at it with angles, you can find that by doing a equals negative omega squared a sine theta. Okay, and that theta is just going to be, oh my god, is just going to be the inverse sine of x over a. Okay, so let's find that angle real quick. All right, so inverse sine of x over a, so 0.05 divided by 0.1. Okay, so there's our angle, sine of that. That's just going to give us 0.5 back. It is. How about that? So 0.5 times our amplitude here, which was 0.1. And then that times omega squared. Okay, so our angular velocity was 4.42 squared. And this does have a negative value because it's going to be accelerated in the negative direction. All right, so we've got an acceleration here of negative 0.977 meters per second squared. Okay. There we go. That was a mess, but we got through it. Hooray us. D. Pendulum bob is held at rest at position B and then released to determine the position of the bob 3 seconds after it has been released. Okay, so we're looking at the intermediate position. So that's going to be x equals a sine theta. Okay, and theta can just be omega times t. Okay, so we've got our omega of 4.42. We've got our time of 3 seconds. Okay, so the angle that it is covered is 13.26 radians. Why did I make it sound like I was going to say something after that? 13.26 radians. There we go. So sine of that times our amplitude, 0.1, and that gives us a displacement of 0.064 meters. Okay, so it has been displaced 6 centimeters. There we go. All right, next, determine the length of the pendulum. Okay, so for that, going back to this period equation, so period of a pendulum is 2 pi root L over G. Okay, we know G, we know T, we're looking for L. So moving this thing around, we got 2 pi underneath the T, squaring that to get that off of there, and then multiplying G over equals L. Okay, so the period of this thing was 1.42 divided by 2 pi, and then squaring that and multiplying by 9.8 because we're assuming that we're near the surface of the Earth. Okay, and we end up with 48.8 meters. It's a long pendulum. 1.42 seconds. So like the one on the stage was only a period of about a second. So it makes sense that it's even longer. All right, checks out. Cool. Next one, number 3. LED provides input power of 1.26 milliwatts to an optic fiber. The output at the other end of the fiber is 1.12 milliwatts. Calculate the attenuation in the optic fiber. Okay, so when we're looking at attenuation, that means we're looking at decibels equals 10 log P2 over P1. Okay, worth noting with attenuation, it's always going to end up being a negative number. Okay, oftentimes it's expressed as a positive number just because it's implied by what attenuation is. It's like a loss in power. So it's often just described as or written as a positive number, even though it's going to give us a negative number in the end. Okay, so 10 log P2 over P1. So our P2 for this one, it's coming out at 1.12. And our input, 1.26. Shut up.
Toby, Eddie, please come to reception. Toby, Eddie, to reception.
Okay, so P2 over P1, taking the log of that and then multiplying by 10. Okay, so that gives us a attenuation of negative 0.51 decibels. Why did I do an uppercase D? There we go, decibels. Okay, and we could just turn that into a 0.51 decibels. Usually attenuation is written as a positive number. Number 4. A cable of length 20 kilometers transmits a signal from one end to the other. The attenuation per unit of length of the cable is 10 decibels per kilometer. 4 repeater amplifiers along the cable each have a gain of 40 decibels. Okay, so looking for the total attenuation caused by the cable. Okay, so it tells us that each kilometer of this thing is 10 decibels. We have 20 kilometers. This is going to be 10 times 20. Okay, so that means we got 200 dB. Okay, negative 200 because it is attenuation. Okay, total gain. Okay, so looking at our gain stuff, we've got 4 amplifiers along the cable, each with a gain of 40 decibels. Okay, so 4 times 40, that's going to be giving us 160 decibels. Okay, which means that our total change is going to be negative 40 decibels. Okay, so it tells us that the input signal has a power of 20 milliwatts. Calculate the output power of the signal from the cable. Okay, so output power, we're looking for P2. All right, we got this dB equals 10 log P2 over P1. Okay, our total change was negative 40. Okay, so we got negative 40 for that. Got to get that 10 out of there. That's negative 40 divided by 10. So what that effectively gives us is negative 4 equals the log of P2 over P1. Okay, now to get rid of a log, all right, it's a function, just like how sine is a function. Okay, if we want to get rid of that, that means we're going to have to take 10 to the power. Okay, so that's 10 to the negative 4th power equals P2 over P1, and I'm out of time, so I'll finish this later. Okay, so finishing this off, looking at number 4, we've already got our 10 to the negative 4th equals P2 over P1. For this one, it tells us that our initial one was, where was it? Oh, 200 milliwatts. Okay, so P1 is 200, and they're just going to be multiplying that over. Okay, so 200 times 10 to the negative 4th equals our P2. Okay, so that is 200 times 10 to the negative 4th milliwatts, and that's just our answer for that. For number 5, I was not asking for any numbers, so you're just going to have to answer it qualitatively. Describe the difference between AM and FM in terms of how the wave is modulated, all right? So that's what the letters in front of the M stand for. AM is amplitude modulated, so it's going to change how big the wave is. You'll end up with your stuff where that amplitude is changing continuously over it. That was a crappy looking wave, but the amplitude goes from like high to low based on the frequency or the amplitude of the signal wave. And then for FM, you're changing the frequencies. So you'll have periods where you're going to have really close together stuff and periods where you're going to have far apart stuff, and it should be the same amplitude the whole way through. Okay, yeah, back to this. So if you're looking at an AM wave, it'll be changing the amplitude. If you're looking at a FM wave, it'll be changing the frequencies. You'll have points where the nodes are close together, point where nodes are far apart. What are the benefits of each of them? So in terms of what the benefits of are, that's not a sentence, stupid. Anyway, so benefits, AM, it's cheaper. It also covers a smaller bandwidth. FM, you get a lot more frequencies you actually end up getting, which means that you can cover a wider range, which means that you're going to have better audio fidelity. Also, it's more popular. AM is for super old people. All right, so AM, cheap, lower bandwidth. FM, better sound. Let's see. Convert your school ID number into binary. Well, my school ID number, when I was in high school, was 3179. Okay? So if you're looking at binary, you've got columns inside of your number that correspond to powers of 2. Okay? So like in decimal, you've got powers of 10 for each digit that you go up. With this, powers of 2. Okay, like if we're looking at this number in base 10, which it is currently in, you've got a 3 in the thousands place, a 1 in the hundreds place, a 7 in the tens place, and a 9 in the ones place. Okay, and every time that you go up to 10, you go over a power of 10. Okay, with binary, you've got a ones place, a twos place, a fours place, an eights place, 16s place, and a 32nds place, a 64th place, a 128th place. Now I want to stop thinking. Okay, so 128 times 2. We'd also have a 256 place, a 512 place. Oh no, I'm going to need more digits. A 1024th place, and a 2048th place. Okay, so if I'm looking at this number, I got 3179. Okay, 2048. Okay, that goes into 3179 one time. Okay, so I have a 1 in the 2048th place. Okay, so I've got my 3179 minus 2048. Okay, so now I've got a remaining 1131. Okay, my next digit is the 1024th place, which goes into that one time. Okay, so now 1131 minus 1024, I'm left with 107. Okay, my next digit, 512. Okay, this doesn't go in to 512 doesn't go in. Oh my God. Hi. You guys can sit down. You're good to go. Okay, so 107, smaller than that number, goes in 0 times. What was I saying? Yeah, okay. 256, smaller than that. Okay. 107 goes into 128 one time. Okay, so 0 there. All right, so 128 minus that. Now I'm left with 21. Okay, so 64 goes into that more than one time. 32. 21 goes into 32 one time. So 32 minus 21. Now I've got 11. 11 goes into 16 one time. 16 minus 11. And I'm left with 5. 5 goes into 8 one time. 8 minus 5. Leaves me with 3. 3 goes into 4 one time. And then I've got a 1 in my 1 space. That was awkward on this video. But there it is. Basically, 3179 is 1 1, 1 4, 1 8, 1 16, 1 32, 1 128, 1 1024, and 1 2048. This is awkward on the video. If you have a question with it, ask it in class where I can explain it better. Because now I'm just listening to the music. I'm getting distracted. Anywho, disadvantage and advantage of a digital signal. So if you're looking at a digital signal, you'll have points where you've got it high and low. Okay? So if each one of the, like if it's split up over time, like if that's a time, 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 that's time, that's time, that's time, that's time. Okay, splitting all that up. All right. You've only got two states. You've got on and off. Okay, so this number, you've just got 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1. Okay, that's the only number it could be. All right, so even after this thing has gone down a wire and it's all fuzzy and its amplitude goes down, you can still tell the difference between on and off because it's only two states. It's drastically different. Okay, which means that they can clean that thing up and it can still end up being the same signal at the end as it was at the beginning. All right, so if you're looking at like, please stop ringing. Please stop ringing. Please. Great. So if you're looking at an analog signal, if you've got like a more complicated wave that's going through there, all right, as that thing is killed by noise, all right, you're going to get like the general shape, but you're not going to be able to return it back to its original state because you've got so many different levels of these frequencies. It's only got two states. You can tell when it's on, you can tell when it's off. Okay, so an advantage of it, it's easier to clean up because it's just a simpler signal. Disadvantage is if you're trying to get like one of these analog things to turn into a digital wave, right? You can only do it in set increments. All right, you don't get the exact wave. You get an approximation. Okay, so you see where these aren't hitting exactly along the line because you've only got certain combinations. Like if each one of these can only go up a certain height to be expressed in decimal or to be expressed in binary. Okay, so it has to abbreviate it. You have to estimate where your waves are at. If you're going to encode something into digital, it doesn't get copied one-to-one. There's going to be less precision, which means that you'll lose some sound or signal fidelity. Okay, so advantage, you can pass a binary wave more easily because noise isn't going to kill it, right? You'll be able to tell on and off, which means the signal can be cleaned up and returned the exact same way it was sent out. Okay, disadvantage, it doesn't have an exact one-to-one relationship of analog. Analog can cover the entire spectrum, everything in between, every single individual frequency from one point to another, decimal frequencies along the way. Binary can abbreviate it, it can estimate it, but it's not going to be exactly right. Okay, so that is a disadvantage. All right, sorry about how weird the binary explanation was. I'm just kind of out of it. I need a nap. Anyway, scrolling along the bottom, you can see all the Patreons of the channel. Please support. Just kidding, there aren't any. I'm an adult. See you later.